Yes, yeah.
Just
Welcome.
to,
Oh, what?
sorry, just
Sorry.
to reconfirm,
Yes,
we
yeah.
have an hour to.
Oh yeah, you guys have an hour.
Just
Welcome.
to,
Oh what?
sorry,
Sorry,
just
sorry.
to reconfirm,
Yes,
we
yeah.
have an hour to.
Oh, sorry about that. Yes, wait. I just messed up audio real quickly. Okay. Welcome to Mega Hackathon's second speaker session. We have it with Sandbox AI. You guys are free to start.
Hello. So I am Jeff Simpson. I'm joined here with Simon Chang. I will be going over the our presentation here, which is how we can sandbox AI, primarily using Vaunt. So just as a quick introduction, as I mentioned, I'm Jeff Simpson. I'm actually a principal engineer at Coachava, and I've been with Coachava for 7 years, working on projects in a group that we call the Office of the CTO, heavily focused on R&D, and I have been the lead developer for the Vaunt project. The agenda is I will give you a brief overview of Vaunt, why we built it, and what AI features we're currently developing, as well as our approach to AI sandboxing. So Vaunt is an open source community engagement tool that gathers open source contributions to display a developer experience level and achievements. And it was designed for two primary audiences. We developed for developers to allow them to showcase their open source level and achievements, and incentivize them to contribute using Vaunt, as well as for organizations or repo owners that can use Vaunt as a tool to drive user contributions and gamify the creation of their developer communities. Vaunt is what we consider a Coachava Studios moonshot project. As I mentioned, I work for Coachava, and luckily Coachava has an organization as a group allows these moonshot projects, which are exploratory projects that aren't necessarily built towards our existing customer base, allows us to try something new, taking on a little more risk. So there are a few different use cases of Vaunt as an organization. If you want to drive stars to your new open source GitHub repositories, you can install Vaunt and add achievements just for starring the repository, which will boost your popularity, allow you to get more visibility into your projects. Additionally, organizations might use Vaunt to track the developer progress of new hires. Because Vaunt can be used on open source or private repositories, you can use it to award achievements to your developers for a number of commits, resolved issues, etc. Additionally, an organization might want, with many different unique contributors, might want to showcase their diversity. They can update their READMEs to show a community board to highlight the different stats that they have within their community. And a developer that contributes to many different open source projects and wants to showcase their experience can update their own GitHub README to show their contributions. So in terms of the Vaunt organization features, as I mentioned, organizations can build out their own custom achievements. We also provide a feature that allows organizations to add a Vaunt bot to display notifications in their discussions when users earn these achievements. Organizations can add a contributor card or community board to their repositories to show their community contributions, and organizations can gain an API access to Vaunt to collect the contribution information that we have and use for their own purposes as well. On the developer side, Vaunt offers free to developer tools. So just like we have the organization boards, we also have Vaunt developer community boards. We have the Vaunt developer community stat cards and achievement cards that can be added to your GitHub README to showcase off developer stats, which allows users to elevate their GitHub profile or visualize their own contributions. So a little bit of how this works. Vaunt behind the scenes has a crawler that collects GitHub data. We collect GitHub data all the way back to 2015 through a GitHub archive, as well as public and private events if a organization installs Vaunt and enables it on certain repositories. Once Vaunt has been enabled on a repository, the repository can also create those custom achievements by placing a file in their repository that Vaunt will crawl, and this sets up the conditions for various achievements. And we have a couple example repositories where we've done this to showcase how repositories can enable these for themselves. And just a brief overview of some of the technical challenges we ran into when developing Vaunt and kind of get to why we're using AI in the future. Initially, when we started doing Vaunt, one of the challenges was getting some of that data that I was talking about. We provide a community board that showcases a repo's contributions all the way back to 2015. We do this through what's called the GitHub Archive event project, which provides BigQuery data all the way back to 2015, as well as we get up-to-date contributions for repositories through the GitHub API, primarily through GraphQL, making authenticated requests on behalf of an installation, which has a rate limit. So we have the challenge of supporting, making sure we're getting up-to-date data without over-requesting data to stay within that rate limit. Additionally, as I was showing in the previous slide, we support a wide range of conditions for achievements. So a repository can award achievements for a variety of different contribution types. So we had to build a custom SQL builder tool for accessing that contribution data from our database. Initially, we started off using a open source Golang tool called Mastermind Squirrel, which worked pretty well. It has a SQL builder, but we quickly ran into some issues because they didn't quite support what we wanted to do. We needed to be able to create templatized queries based on those various conditions we wanted to support, which led us to actually build our own templatized query builder for Go called Tequila, TQLA. And we actually open source this. So this is open source on Vaunt.dev under TQLA, and also has Vaunt achievements enabled on it as well. And then another challenge was that job scheduling. As I mentioned, we have the rate limiting. So we built our own job scheduler in-house for Vaunt that enables us to get up-to-date data without running over rate limits by queuing and running jobs as quickly as we can. And then one other technical challenge we ran into was the ability for contribution cards to be displayed on GitHub READMEs. We needed to support SVGs. So our APIs in Vaunt, a lot of them are updated to be able to return those SVG images. Initially, we started off by embedding PNGs within the SVG, such as for like those achievement images. However, that ballooned up the size of those SVGs, which often got them blocked due to rate, limiting by GitHub. So we came up with some optimizations to scale down the sizes and enable those to be embedded in READMEs without causing like large load times or anything like that. And then additionally, we're still running into technical challenges on streamlining onboarding because Vaunt requires steps both on the organization and the developer side in order to actually take advantage of all of Vaunt's features. And that led us to, we started thinking about how we could use AI to enhance Vaunt and answer some of the technical issues we've come across. So, obviously within the last few years, LLMs and AI have been blowing up. So we tried to figure out how can we take AI and enhance Vaunt with it. So these were actually some of the things that were added to our Vaunt roadmap thanks to AI. And I'll talk through a couple of these, but basically, some of our initial ideas were to use AI and LLMs to create a chat with your repo feature or a chat application, so that you can use our Vaunt data along with an AI to allow you to ask questions about contributors, contributions, etc. We also are considering some features in the AI code generation side to allow you to automatically generate READMEs, contributor guidelines, even those achievement manifests, just straight through a chat application with an AI. As I mentioned, we already have a Vaunt bot that can post in your discussions to ping when a user awards achievements. We've considered enhancing this to also be able to make PRs into your repositories to update when certain milestones are reached, or to make changes as needed. Additionally, right now for achievements, repositories have to supply their own icons. So we've considered using AI image gen technology to allow achievements to automatically be generated, as well as using AI as part of our community boards to allow repository discovery through Vaunt. And then lastly, one was we wanted to consider using our platform APIs to allow Vaunt data to be accessed directly through a chat application, as many of the LLM chat applications are becoming very popular. And so that's where we actually decided to start, was how do we expose our platform APIs through a chat interface to enable users or organizations to access that data. A couple of the reasons why we decided to start here is we already have a wide variety of public APIs that support Vaunt, such as those different contributor cards. So as I mentioned, you can embed SVGs into your READMEs, and both as a developer and an organization. Well, those SVG endpoints also support just returning plain data. And that actually works really well with AI to provide another interface into accessing that data and getting some use out of it. So what we decided to do was to come up with a way to build AI tools and functions to take advantage of that data and provide it to users, primarily through like a chat application. And just to give a brief overview of some of the high-level AI concepts we've come into touch with this is, these AI LLMs are largely based off transformer architecture. If you're not familiar, you can check out some of the multi-head attention mechanism information that's out there. And additionally, AI, there are a wide variety of model formats. Some of the ones that are becoming more popular now, GGML and GGUF formats, actually allow for basic hardware, such as like a Mac laptop, to run local models, potentially through like Olama or other like LM Studio type systems. In terms of tokenization, this is, if you're not familiar, this is the basic process of how these LLMs are converting plain text into tokens to be able to train and produce generation with text generation LLMs. And then some of the newer concepts are function calling. So these LLMs have the capabilities to both generate executable functions, or run functions through structured output like JSON to enable app integrations with a chat app. And this highlights how there are real-world examples of being able to chat with an LLM and execute code that accesses either an API such as Vaunt or others to enhance their capabilities. And then some theories around this are, we are able to merge LLM execution with dynamic tool creation to create these AI workloads and create agentic workflows. So where we're kind of focusing with Vaunt and AI in general is on that function calling. So function calling allows LLMs to invoke structured functions to interact with an external system or tool. And that bridges the gap between LLM pure text generation capabilities and the ability to interact with existing systems such as APIs. Some example use cases, there are LLMs that you could use an LLM to generate Python code to check if a number is prime, which would generally execute on its secure runtime. And an example use case that we actually did at Ojava is we incorporated an LLM app to go from natural language to SQL to give customers a way to query an API and get information on their data. So and interact directly through a chat interface. So we already had a query API that was exposed, and in order to let users use it without having to know how to write the queries, we developed a chat app that does the natural language to SQL. And function calling relies heavily on a few different things. Prompt engineering, those system prompts that you provide to an LLM that tell it that you can give it instructions on the context on how to generate function calls. It requires multi-step reasoning. So the LLM needs to determine if a function actually needs to be called. The inputs need to be produced and validated. Then it needs to call the function and return that input back to the LLM. And any contextual information that's required needs to be provided through that context. So some of the pros of function calling, it allows integration with existing workflows and systems, as I mentioned, like public APIs, etc. It's scalable. It facilitates modular design where functions can be reused or extended without having to rewrite code for every different API. It provides a structure. You can use JSON or executable code, making outputs usable with LLMs. It allows interoperability by going from your LLM to a system that wasn't necessarily designed for it. It allows adaptability as functions can dynamically be swapped or updated without affecting the core code. It can provide security, which is one I'll be focused on here in a few minutes, because what it does require is you need to make sure you're using a sandbox execution environment if you're going to be able to execute untrusted code. Additionally, it provides flexibility, cost efficiency, and error handling. If you, as LLMs are not equipped to handle some errors, you can use a system through function calling to gracefully handle failures. And it will enable automation, as you can chain these function calls together to create these workflows. Some of the cons of function calling, as this technology is kind of new, there's a lack of standardization. So there are a lot of emerging solutions, but it makes it a little tricky because there's not one set standard. There is limited language support, which is getting better, but a lot of these frameworks focus on Python. So function calling usually is limited to the Python language. There are security concerns. So as I mentioned before, if you're not using a sandbox, any AI-generated code potentially has risks of breakouts or malicious behavior that you need to avoid. It can increase deployment complexity because not only do you now need to deploy a chat app, you also need to deploy a secure runtime. And it does result in some fragmentation, as you will have to consider all the various tools and LLM models that you need to choose between, and some of them require very specific formats. So just to give a little overview of kind of what I've talked through, the general architecture, this is a very simple form of how function calling might work for an AI service, is you would offer a user interface where a user can enter a natural language prompt, which would go to your AI service. The AI service would do some sort of context enhancing. So it would add like the system prompt, some of those examples as we talked about. It would pass that full context to an LLM. The LLM would generate text if it decides that a function call needs to be made. It's going to be generating those functions and parameters that it then sends back to your AI service. The AI service then can do input processing or whatever. It will actually make the function call, which may be local or through a remote API. It'll take the results of that function call, send it back to the LLM with the original prompt, and then the LLM can use both the results of the function call and any initial input to decide if that answers the user prompt, comes up with a final response that goes back to the AI service and back to the user. So some of the emerging solutions, as I mentioned, there's a variety of standardization around function calling. But some of the emerging solutions include Meta Llama's 3.0 or 3.x series of models that support tool calling with either built-in JSON-based or custom-defined tools. And the nice thing about that is those Meta Llama models can be run locally with that GGUF format, as I mentioned before. And then there's also Anthropic's Model Context Protocol, MCP, which is becoming very popular lately. It provides a universal standard for tool calling through JSON RPC, and it's primarily focusing on interoperability across applications and LLMs. And then another one that we really like is Hugging Face Small Agents, which is a lightweight framework for code agents with Python code generation, which combines tool calling and runtime executed Python scripts. And then that takes us to our approach. So we've been focusing on how LLMs can be used to orchestrate local and remote tool calling through protocols like MCP, and executing secure runtimes with implementations like small agents and E2B. And while these tools offer tremendous benefit to an LLM, each has trade-offs that have to be considered. One of the other things that we are leveraging is a technology called WebAssembly, which has the potential to reduce some of those trade-offs. We believe that WebAssembly, also referred to as WASM, unlocks an LLM's potential by providing that secure cross-platform environment to execute AI-generated code with unmatched speed and security. And WASM has been designed as a portable compilation target for programming languages, that enables the development of on the web and for client and server applications. So we proposed WASI agents, which is a set of WebAssembly interfaces that introduce the standardized way for AI agents to be built with WebAssembly components. So WebAssembly-based framework for secure and modular AI function execution is where we landed. And that is the key features of this is it provides that cross-platform compatibility. So you can run on browsers, servers, or edge devices. WebAssembly has that built-in sandbox security because WebAssembly runtimes isolate function execution to minimize risks. It also keeps in line that modularity as it allows WebAssembly components to be interchanged with AI agent components. And it allows interoperability as there is a WebAssembly interface types definition, which standardizes tool definitions. It allows systems to define an interface and allow users or developers to develop directly for those interfaces. So some of the benefits is it combines performance and security. It supports multi-language AI inference through WebAssembly standards like WASI-NN. It also reduces the dependency on middleware like MCP. So our vision is to enable AI agents to dynamically orchestrate secure and efficient workloads using WebAssembly. And so what makes WebAssembly unique for AI? Like AI, WebAssembly is actually undergoing rapid innovation currently, and it's expanded beyond its initial web use case to server-side implementations. And this has been made possible thanks to the WebAssembly Systems Interface, WASI, which is a collection of standards for running WebAssembly modules outside of web. It was designed to provide that secure standard interface for any language to be compiled to WebAssembly and run anywhere, browsers, cloud, or embedded devices. To date, WASI has seen 2 milestone releases, known as 0.1 and 0.2, often referred to as WASI Preview 1 and Preview 2. The key differences between these releases is that the WebAssembly binaries with WASI 0.2 may now be compiled to components built according to what's referred to as the component model, or modules built to a core WebAssembly specification. So for reference, components can use WASI 0.2 in the component model to allow composability and interoperability, meaning that WebAssembly components compiled from one language, like Rust, can communicate or be combined with a component compiled from another language, such as Go. And this has set the standard for the future of WASI. Now, modules were the original implementation of the APIs from WASI 0.1. And so the earlier stage of WASI's development, since WASI 0.2 was released in February 2024, WASI 0.1 support is still more widespread among WASM runtimes, and it is widely used in production today. However, the component model introduced in 0.2 introduces that concept of a component and allows you to create a wrapper around core modules, specifying its imports and exports with what I mentioned before, which is the WebAssembly interface types with definitions, which allows you to create interfaces and worlds. And just to give an example and show kind of what this means, below is a basic WIT example of an add interface. The WIT definition defined on the left defines an add interface with a single add function, and it later exports this interface through an adder world. And this creates a common interface for implementations of the adder world and how callers that want to use this should be able to pass parameters. And on the right is an example of how you could actually implement this with Go. With very few lines of code, this could be compiled to WebAssembly. And just as a sneak peek on how this is coming to be used in Vaunt, we are currently working on a project that is not yet open source, but we're working towards it, that uses WebAssembly, those WIT definitions to define how AI models and AI agents can be utilized with any LLM. One way we're doing this, particularly with Vaunt, is to create agents that have access to our Vaunt APIs to provide a tool that would allow a chat application to interact and use the data that we expose through Vaunt. So on the left here is in Go a very basic implementation of an AI agent that interacts through a series of turns with an LLM. It takes in a user prompt, calls the model compute, which is actually the LLM code prediction. If the LLM responds back that it is a tool input, particularly in this case, the HTTP tool for Vaunt, it will take the input of the message, reach out to a Vaunt API, format that data into a response to go back to the LLM to allow the LLM to keep computing. And on the right is an example of how a model might be defined with this Vaunt tool, as well as with some system prompt context. And all this can be compiled to WebAssembly into a single agent component that could run on an environment that supports this model agent framework. And then just to give some of the resources on things that I've gone through, if you're interested in any of this, I'll have some links, or I'll have some emails that you could reach out to, and we can provide some of these resources. But we've gone through WebAssembly, so a lot of the things I talked about today, are provided to us through Waffentime, the component model, WIT definitions, WebAssembly composition, as well as WIT bingen, which is how we create those bindings. Additionally, with Rust, we've utilized Llama CPP and WIT parsing. And for compiling Go to WebAssembly, we've utilized WIT bingen Go. And then, like I mentioned, for some Q&A, if you have any questions, feel free to reach out to Vaunt on X at Vaunt.dev, as well as my email, Simon's, and Ethan Lewis, which is our CTO. Our emails are provided here. If you have any questions, feel free to reach out, or if you would like any of these resources that we've talked about, or potential information on this new project that we're working on, again, feel free to reach out. Thank you.
Okay, so that's it with your presentation?
Yes.
All right, well, thank you so much for the presentation on AI and your approach on sandboxing and using AI. We are very fortunate to have you guys here. And yeah, that's it. Well, thank you. Thank you very much.
Thank you.
Thank you.
Thanks for having us.
Bye.
Bye.
And that's it with our second guest speaker. We have another speaker happening in about 3 hours, presented by an FRC guest speaker at 3 o'clock p.m. EDT. Thank you.